Okay, well, let's get started. Today we are talking on, last week we left off talking about confidence intervals. We talked about the dog and the invisible owner going for a walk, and we said because we see the dog, we can infer where the owner is, right? And we might not be 100% confident about where the owner is, but we can be pretty confident that the owner is within a reasonable range of the dog. Okay, and this was kind of the idea behind confidence intervals. So let me just set this up here. Confidence intervals. And we said the big idea here is we observe a sample, and based on what we see in the sample, we will try to make statements about the population. And this is really actually statistical inference. All right, let me have you guys settle down as we get started. And kind of the running example is that, we've got a large bucket of M&Ms, okay? And in the bucket, okay, so we do not know the exact count of M&Ms. In the tub, or this would be our population. We do not know the exact size of the population, and we do not know the exact proportion that is, some trait, such as red. That's our P. So we don't know that, so we say, the population proportion, P, is unknown. Okay, and what we do is we take a random sample, and in this case we're going to take, out of here we take a scoop. We say, we get a scoop of 150 pieces of candy, and we'll say that we count 28 red pieces of candy. And so the question is, so my data is that the sample has n equal to 150, x equal to 28, and that means my sample proportion, p hat, is 28 divided by 150, which is equal to 0.18667. And our question is, what does this tell us about P? Okay. And when we were talking about the dog, we said if we see the dog, because we know the dog stays close to the owner, if I see the dog, even though I don't know where the invisible owner is, I can be confident the owner is nearby. Similarly, we said that if we see P hat, because we know P hat follows a normal distribution, meaning that most of the time P hat stays close to P, if I see P hat, I can be confident that P, the population proportion, is nearby. That's what we said. All right. can I flip to the next slide here? Yes. Here I go. All right. So we said because of the central limit theorem, we know that p hat follows a normal distribution centered at p. And what that means, so this means most of the time p hat is close to p, okay? And therefore, this means that if we observe a particular value of p hat, we can be confident that p is nearby. Okay? And so if we make a 95% confidence interval, we can say something along the lines of, I am 95% confident that P is within, and I know when I first introduced the topic I said within 2 standard deviations of P hat, but what we're actually going to say is we're going to use the value 1.96 is within 1.96 standard deviations of P hat, okay? Or I can say I am 95% confident that P is between P hat minus 1.96 standard deviations and P hat plus 1.96 standard deviations. So likewise, you know, when we were looking at the dog on the field, we said if the dog is at 30, we can be confident that the owner is between 28 and 32, and we did that by doing 30 minus 2 and 30 plus 2. Similarly, we do, you know, I can be confident that P is between P hat minus 1.96 standard deviations and P hat plus 1.96 standard deviations. Was there a question?
Yeah, why is it not 2? Were we always rounding up to 2?
This is my exact next slide. I'm going to tell you why 1.96 and not 2. So the 2 came from the empirical rule where we said, you know, 68% of the time we're within 1 standard deviation of the mean, and 95% of the time we're within 2 standard deviations of the mean. If we want to be more precise, we should use 1.96. And so I'm going to flip to the next slide, and we're going to ask, you know, why are we using 1.96? Okay, so why 1.96? Okay, and so this comes from the normal distribution. We look at the normal distribution. And so here I've got the normal distribution. And let's say, I'm going to put 0 in the middle. Let's say I want 95% in the middle. If I want 95% in the middle, I'm going to have, if I want 95% in the middle, how much will I have in each tail over here? How much do I have over here, and how much do I have over here? I'm going to have 2.5% in each side, right? Because we need a total of 100%, so I'm going to have 0.025 over here and 0.025 over there. Right? And so if we go to the z table and we ask what is the value that's going to give me 2.5% in the lower tail, okay, so we go to the z table, the z that corresponds to area equal to 0.025 is z equal to negative 1.96. And likewise, if I look up positive 1.96, I'm going to find area to the left equal to 0.975, meaning the area up here is 0.025. Okay, so I'm going to have z is basically plus or minus 1.96. So if I look up probability that z is less than positive 1.96, that gives me 0.975, which also corresponds to 2.5% there. So I got 1.96 and positive 1.96. Now the empirical rule, for the sake of nice and easy numbers, we were just using 2. We said 1.96, that's pretty close to 2, so we're just going to say 2 standard deviations. But the true value is 1.96. Okay? Is that all right? Okay, so I'm going to give you a clicker question here. And the clicker question is, let's say I want this 80% in the middle. And the question is, what is the z that I'm going to use? So for an 80% confidence interval, what is the critical value z that I will use? Okay, so we want 80% in the middle, and so your answer choices are okay. You can consult with your neighbor to decide. Let me get the clicker software running here. And I'll let this run here. Okay. So we'll let that run. I'm going to pause. Okay, let's take a look at how you guys responded. And indeed, the correct answer is C. Okay, and so I'm pretty sure you guys figured this out because so many of you got it correct. But the idea is, if we're going to have 80% in the middle here, we want 10% over there and 10% over here. And so looking into the z table to find the value closest to 10%, the value that I find is 0.1003. That's in the row negative 1.2 and the column 0.08. So the z that I use will be, negative 1.28 and positive 1.28. So basically I just use 1.28 there. All right. Okay, is that good? And so, we could apply this line of thinking for any kind of confidence interval. So here we looked up numbers for an 80% confidence interval and a 95% confidence interval. If you wanted to find values for a 99% confidence interval or a 75% confidence interval, you could do that. I'm going to just kind of give you the 4 of the most common choices for z. Choices for z star, the critical value. So we have for 80% confidence, which is the problem that you guys just did. For 80% confidence, we have z star equal to 1.28. For 90% confidence, if you follow the same line of thinking, you'll get z star. You'll find two values that are very close, 1.64 and 1.65. So we split the difference and we go with 1.645. For 95% confidence, we use z star is equal to 1.96. And for 99% confidence, we will use z star is equal to 2.58. Right? And technically, if you wanted to create a 93% confidence interval, or a 65% confidence interval, or just some arbitrary number, that is allowed. There's nothing wrong with it in of itself, but it's just not very common. As people, we kind of like these nicer numbers, 80%, 90%, 95, or 99%. These are probably the most common choices. And so with these four values, that covers almost all of the confidence intervals that you might make for proportions. But yeah, if you want to make a 97% confidence interval, that's allowed, okay? It's like ordering a 3/8 pound hamburger. It's not very common, but you can do it, all right? In general, or actually, so yeah, let's just talk about the general form of a confidence interval. For the population proportion P, based on a sample with P hat. Because that's what we're doing, right? We take a sample with P hat and we're creating a confidence interval for P, and we would say something like, we are blank % confident that the population proportion P is between, and we would do P hat minus Z star times our, I'm going to write standard error, and P hat plus Z star times our standard error, okay? And, we can combine these two things, P hat minus Z star and P hat plus Z stars times the standard error. We can just write P hat plus or minus Z star times the standard error. SE, SE is the standard error, which is equal to the standard deviation. I think on the previous slide I just called it the standard deviation. But if it's the standard deviation of the sampling distribution, then the formal name would be the standard error. Okay, so that's what we have. So the standard error is the standard deviation of the sampling distribution, and oftentimes we combine the plus side and the minus side into just one formula or one equation here. But keep in mind, you're going to get two values. When you create the confidence interval, you're going to get the value where you subtract it, and you're going to get the value where you add it. So you have a lower bound and an upper bound. Okay, so maybe I might write this here. This is going to be our lower bound, and over here this is our upper bound for the confidence interval. Yes, question?
I have a question with 90% and 99%.
Yes.
For 90%, you took the average between 1.64 and 1.65, but 99% you took the average between 2.57 and 5.8. Why is it different? Why is it not consistent?
That's a good question. I guess we were just kind of lazy and we just rounded up to 2.58. I mean, the true value is probably like 2.576, but just to kind of keep our lives easy, we just said 2.58. But, yeah, if we wanted to be super precise and pedantic, we can extend a bunch of decimal places. That's true. You know, the choice of 1.645, we often go with this because if you look at your z table, it's like exactly the same distance between 1.64 and 1.65. Whereas the other ones, it's a little bit closer to one of these values than the other one. Yes?
For the other one is 9949 and 9951.
You know, if we extended more decimals in the table, it's not exactly in the middle, but yeah, I mean these are good observations, but generally, unlike other mathematics disciplines, statistics is a little bit more loose with our terms. Everything's kind of an I mean, this whole thing that we're doing, central limit there, it's an approximation anyway to begin with, so all right, let's talk about that standard error term, okay? So we said, what is the standard error? So what is the standard error equal to? So we said the standard error is the standard deviation of the sampling distribution. It's the standard deviation of the sampling distribution. And do you guys remember what the standard error is equal to? The standard error is equal to the square root of, should be somewhere in your notes, right? You should know this. You will need to know it for Friday. The standard error, or the standard is of the sampling distribution, this is equal to square root of p times 1 minus p, yes, times 1 minus p divided by n. Okay, so I mean you'll need to know that for Friday, okay? Do you guys spot a problem here with this formula for the standard error? This is the formula for the standard error, but is there a problem with us trying to use it?
Don't know P.
We don't know p. That's the problem, okay? So there is a problem. We have a problem. Okay. We do not know the value of p. So what should we do? We don't know what p is.
Substitute P hat.
That's exactly what we're going to do. We're going to plug in p hat as our best guess for p. Okay? So we don't know the value of p. So, our solution, we plug in p hat as our best guess for p. And that makes sense, right? And it turns out that there's no real negative consequences of doing this, okay? Sometimes you think, we're just, I don't know what this is, so I'm going to just take my best guess. And sometimes when you guess and do things, mathematically there's some consequences. It turns out mathematically the consequences, we don't really have to worry about it, so we can move forward with this. We don't have to do any kind of compensations. Later on, we do something similar when we're dealing with means, but it complicates things and we have to compensate for it. But and so this works out. I'm not going to prove mathematically that it works out, but that's what we do. Okay. So now our confidence interval. For the confidence interval, our standard error is going to be equal to the square root of p hat times 1 minus p hat over n. And it looks almost the same, but they're not the same. Right here we use hats, and over here there's no hats. Okay? So the confidence interval is p hat plus or minus z star times the standard error, and our standard error is equal to the square root of p hat times 1 minus p hat over n. Is that good? So this is how we make a confidence interval All right, let's try this, apply this to kind of our example that we've been using here. All right, so we'll say we have drawn a random sample of 150 pieces of candy. $150 M&Ms from a large bucket. Okay, and we count 28 red pieces. And so I'm going to say make a 95% confidence interval for the proportion of red pieces in the bucket. So we're going for the population proportion, right? So make a 95% confidence interval. And the question, we're going to have a clicker question here. Here is, what is the lower bound of the confidence interval? Okay, and so here are some answer choices. Okay, and you can go ahead and try this out. You can consult your neighbor. Make sure you guys got this. Okay, so if you were watching online, or if you're watching online, I'm going to reveal the answers that everybody selected. So pause the video. Okay, and I would say that is correct. Okay, answer choice D. All right, and so, well, I'll go over the answer quickly. So the confidence interval is p hat plus or minus z star times the standard error, and we said the standard error is equal to the square root of p hat times 1 minus p hat over n. Okay. We have determined that p hat is equal to 28 divided by 150, giving me a p hat of 0.18667. Therefore, my standard error is going to be the square root of 0.18667 times 1 minus 0.18667 divided by 150. And when I punched this out, I got 0.0318 as my standard error. Okay, so that gives me this part right here. I need to figure out my z star, and that's going to be based on 95%. So for 95% confidence, what do I have? Z star is equal to 1.96. Okay, so that's what we've got there. We've got z star and we've got p hat. So my lower bound is going to be p hat minus z star times the standard error. This gives me 0.18667 minus 1.96 times 0.0318, and when I did this I got 0.1243. So that's my answer there. Answer choice D. Okay. The upper bound will be 0.18667 plus 1.96 times 0.0318. And that gives me 0.249, yeah, something like that. Okay, so my 95% confidence interval is basically 0.1243 to 0.249. Is that okay? All right, and so let me just put up the interpretation for this. And this is, I think this is the important part for a confidence interval, is being able to properly interpret the confidence interval. And so I would say something along the lines of, I am 95% confident that the proportion of red candies in the bucket, that is, you know, the proportion, population proportion P, is between 0.1243 and 0.249. Okay, so I'm 95% confident that if I dumped out all of the candies in the bucket, counted all the pieces, counted all of the ones that are red, and get the exact proportion P, that exact proportion P is going to be between 0.1243 and 0.249. Is that all right? Okay. If I wanted to be more confident about getting the true value P within my range, would I make my interval wider or narrower? I would make it wider, right? If I want to be more confident that my interval happens to get the true value of P, I want to make it wider, okay? So if I want to be more confident that my interval contains the true value of P, I would make my interval wider. Okay, and this is reflected in the fact that to increase my level of confidence, my values of Z star get larger. And when I decrease my levels of confidence, my values of Z star get smaller. Okay, because P hat and the standard error would remain the same, but changing the values of Z star reflect the level of confidence. And so when I want higher levels of confidence, this gets wider. In general, though, a narrower interval is desirable, okay? So a narrow interval is generally more desirable, but it comes at the cost of lower confidence. Okay, because if I wanted to be 100% confident about the proportion P, I could just say I'm 100% confident, you know, whatever it is you're talking about, that proportion P is going to be between 0 and 100%, okay? I can be 100% confident about that. But that's not a useful thing, right? You know, if we're doing some budget planning for next year, and I said, okay, well, how much money are you going to make next year so we can start planning out a budget for you? You say, well, I'm pretty confident it's going to be somewhere between 0 and $1 million. That's not very helpful in terms of planning a budget. And so, you know, if you can say, well, it's going to be between 30 and 35,000, that's a lot more useful in terms of planning out a budget. If you can make a more narrow interval, then it's generally more useful because you have a better idea of what value you're dealing with. The trade-off is you're less confident about that range that you've given me, okay? And you know, the only way you can have a narrow interval and maintain high confidence is by collecting more data. And that's reflected in the formula for the standard error. Inside you have square root of p times 1 minus p, or p hat times 1 minus p hat, divided by n, meaning the size of your sample plays a role in your standard error, and it's in the denominator, so bigger samples will shrink that value down. All right, I got a few more things, okay, to say, and I'll try to squeeze it in just our kind of our last minute here. So this is our confidence interval. So my confidence interval goes from 0.1243 to 0.249, okay? So the first question I can ask is, do we have evidence that the population proportion P population proportion P of red candies is different we'll say from 28%. Okay, do we have evidence that the proportion of red candies is different from 28%? What do you guys think? Yes? No? Maybe? Okay, well, if we look at this kind of represents our range of plausible values. Okay, so is 28% within my range of plausible values? It is not. Okay, so our answer here is yes. 28% is not, or I'll say is outside of the range of plausible values of P. Okay, and therefore we would say we do have evidence. I'm going to go over by like 1 minute here, and I apologize. We do have evidence that P is different from 28%. Okay. I'm going to ask a very similar question, but this time instead of 28%, I'm going to ask about 20%. Okay? Do we have evidence that it's different from 20%? Okay, and so the answer to this question is no. 20% is within the range of plausible values. Okay, so P could be 20%. Okay, and we would say we do not have evidence that it is not 20%. Okay, and I know that's a bunch of double negatives, but we do not have evidence that it is not 20%. Okay, I got one more thing. I know, all right. That it is not 20%. Okay, and then the last question that's similar but different from all of this is, do we have evidence that it is 20%? Do we have evidence that P is 20%? Okay, and the answer here is also no, all right? Because even though here we said we do not have evidence that it is not 20%, that is not the same thing as saying we have evidence that it is 20%, okay? So we'd say, you know, a confidence interval cannot provide evidence that P is any particular value. The only way we can get a particular value is to dump out the entire population, count everything up, and count the exact proportion ourselves. That's the only way we could say P is a certain value. Whenever you create an interval, it's just a range of plausible values, and it's never saying that it is a particular value in that range. We're just saying all of these values are plausible, okay? So So that's what we're saying here. Do we have evidence that P is 20%? No. A confidence interval cannot provide evidence that P is a particular value. Okay, we'll end there.